Thank you very much. It's a great pleasure to be here. It's my first time in Belgrade. Very happy to be here. You're very lucky to live in a part of the world where mathematics gets such respect. And a big round of applause to the organizers who've put on this incredible evening for everybody. So if I could have my slides, please. So what I'm going to do is perform two mathematical card tricks for you, but also do some other stuff, a little bit of other stuff. And I want to tell you first about the person who introduced me to mathematical card magic. When I was a teenager, I read some books by Martin Gardner. He's very famous. He wrote a lot of books a long time ago, but he lived a long time also. He lived to 95, and I had the good fortune to meet him in the last years of his life and get to know him. And this talk is very much inspired by him. So I'm going to talk about Mathemagic with a deck of cards. And my name is Colm, and I call myself Card Colm on the web and on Twitter and so on. So you can find all this stuff also online. So you can learn a lot of mathematics from a deck of cards. A deck of cards is an interesting and quite cheap laboratory, much cheaper than doing high-entry physics or chemistry or biology. For a couple of dinar, you can get yourself a deck of cards and learn a lot of mathematics and have a lot of fun, too. So I'm going to show you a couple of tricks that work because of mathemagical principles. But the way I present them, it's in a more entertaining context. And usually when I show them to people, especially young people at first, they don't believe me. My students never believe me when I say this works because of mathematics. And then later on, I show them the mathematics. Well, tonight I'll show you the mathematics. And as I said, it's very much inspired by Martin Gardner. And he lived a long time, from 1914 until 2010. And you can use mathematics card tricks to spice up your classes if you're a teacher, and also parties. We heard earlier about how you can have fun at a party by finding two people with the same birthday, which most people don't expect. You can do similar things with cards. So here is the man that I call the best friend that mathematics ever had. Because other than Euclid, nobody has written works which are as much read. Martin Gardner wrote a lot of books, and they are very much read, have been for 50 or 60 years. So many generations of people all over the world read his books. And I think he had a big, big influence on mathematics. Interestingly, he was not a mathematician. In fact, he had no training in mathematics, which is very surprising. He took high school mathematics in America in the 1930s, which would have been algebra, geometry, trig. That's it. There was no calculus in those days for people of that age. And yet, he inspired so many people. He inspired people in his writings who grew up to be mathematicians and physicists and philosophers and magicians and computer scientists and so on. And I call this Martin Gardner standing by every word he ever wrote. Because actually, this bookcase, you can see 4 shelves of books. There are 6 shelves of books. Most people don't read that many books in one lifetime. He wrote all of those books. That's how productive this man was. He actually wrote 101 non-fiction books on mathematics, puzzles, physics, philosophy, and Alice in Wonderland. He was very fond of Alice in Wonderland and The Wizard of Oz, and the annotated Alice in Wonderland he wrote a long time ago, and that started this trend of annotated books. He was the first person to do that back in 1960. And his friends and associates included people like M.C. Escher, the incredible Dutch artist who used mathematics in his artwork, Salvador Dali, who consulted with Martin Gardner in the 1970s about 4-dimensional geometry, and Isaac Asimov, who wrote about 300 books. They were all friends and associates of Martin's. So he wasn't a mathematician, he was a journalist, and he knew people in many areas of the arts, as well as mathematicians and scientists. And you can find him on Twitter. What would Martin Gardner tweet? Well, he didn't quite make it to the Twitter age, and he didn't like computers very much. But we feel that he would tweet nice little short things about, check out this interesting card trick, or this interesting optical illusion, or some Escher art, or whatever. So that tweets several times a week, WWMGT. We encourage you to investigate that. Now, he wrote about 300 columns for Scientific American, which was a very popular magazine, still is, and 50 years ago, 40 years ago, when he was writing for it a lot, it had over 1 million readers. And we know that a lot of those people were buying the magazine to read him. And when he stopped writing for it, the sales went down. And Scientific American sales have never gone back up again. So a lot of people read it because of his very good columns. He wrote for about 25 years, very entertaining columns. You can buy them in books. Some of those books have been published here in Serbian. Many more are available in Russian, Polish, and so on. And you can also buy them all on a single CD-ROM. Okay, sorry, too fast. So among the topics that he introduced a wide reading public to are things like Escher art, the Conway game of life, the fact that every map can be colored with 4 colors, Fermat's last theorem, we all know about it now. Back in the 50s and the 60s, the general public did not know about it. He introduced the general public to these things that are now famous. He also was the first person to write about fractals for the public and cryptography, and he loved paradoxes. As a philosopher by training, he loved paradoxes. And of course, mathematical card magic. He's also, in fact, famous before writing about mathematics. In the early 50s, he wrote a book called Fads and Fallacies in the Name of Science, which was about fake science and fake medicine. And he debunked all that stuff in 1951, a long time ago. And he said back in 1948 that things like Scientology wouldn't last very long. Well, here we are in 2017. It's still going strong. He did not like that. So he was first and foremost a skeptic. And among his friends were Carl Sagan, who helped him found the skeptical movement in the mid-1970s, and James Randi, who's about 90 now, and he's still very active in that field. But I want to talk about cards, and I want to make sure we all understand what's in a deck of cards. So cards have various values. There's 52 of them. This one here is the 4 of spades. This one here is the 6 of hearts. This one is the Jack of hearts. So you probably know that there's 52 cards in a deck, and they come in 2 flavors, red and black. There's 26 red ones, and there's 26 black ones. And if you look at the different colors, they split up into 2 suits each. So the black cards, half of them are spades, half of them are clubs, and the red ones, half of them are diamonds, and half of them are hearts. And in a few minutes, and again a little later in the talk, I'm going to ask some volunteers to come up and help me. So I'd like some people who would be interested in helping and who are familiar with these card names. They need to look at cards maybe and remember them and know the names and so on. So there's 13 in each suit, and it's common to start. We consider an ace to be a 1, because if you look at an ace, it just has 1 symbol on it. So an ace counts as 1, it's low. And that's followed by a 2 and a 3 and so on, 4, 5. And then it goes up to Jack, Queen, and King. And for the purposes of mathematics, since the Jack comes right after a 10, we consider the Jack to be 11 numerically. And the Queen is 12. And a King is 13, okay? Now, this is a new deck of giant cards that I only opened today, so they're not very well mixed up, but it doesn't really matter, because I'm going to shuffle them more in a minute. I'm actually going to leave those ones out because I need to explain something with them later. But I'll shuffle the rest of them here. And I don't have big hands to shuffle these the usual way, but we'll see what we can do. Maybe I'll try shuffling them this way. These are very big cards. Let's see. So I'm shuffling the cards like this, and I push them together, and I can do this a few times. And then I'm going to ask for some help. Now, not everybody here maybe likes cards, and that's okay, because I also have a couple of things for people who don't like cards. So if you don't like card tricks or cards, it's okay. I have something else for you. And actually, if you're thinking now, he's going to do a card trick, I don't like card tricks, I have a special exercise. If you're young and you have some paper and a pen, I'd like you to try this. And if you succeed, I will give you all the money in my wallet. All the money in my wallet. Now, there's not a lot there, but there's enough. You know, there's US dollars, there's euros, there's dinar, and there's British pounds. So, you know, there's probably about $200 worth of money. And whoever succeeds in doing this, before I finish, can have all the money in my wallet. And I have some people standing by, Colin and James and so on, who'll be checking your work to make sure it's accurate. So here's what you have to do. List all possible arrangements of these 52 cards. So, you know, they can be arranged. That's the order that you get them. Maybe when you start the deck, this is a different order. So if you can make a list of all of those, please, in the next 25 minutes or so, there'll be a special prize. And if you don't like cards, it's okay because I have a completely different exercise for you if you don't like cards. And that is to list all possible arrangements of the 52 white notes on a piano. Totally different problem, right? So if you can do that, we don't want any repeats, but if you actually do it using repeats, you get bonus points. If you succeed that, I'll give you all the money in Colin Wright's wallet also, okay? So, a good offer here. Okay, so this is the trick. I've shuffled the deck. I'm going to shuffle it one more time, and I need two people to help me. And they need to be people who can add up numbers, because, for instance, two cards are going to be picked. And if these were the cards, I would ask you to add up the numbers and later to tell me. So in this case, 10 plus 10 is 20. If the cards were these two, you would add them up, and what would the total be? 8, right? 7 plus 1. An ace counts as 1. That would be 8. So I need two people who know the card names and the suits. We need to remember the suits. So if two people can please come forward to help me. Do I have two people who'd like to help? Excellent. There we have one. Please come on up. What's your name?
Alex.
Alex? Okay. Alex, and your name? Holgen. Okay, thank you. So I'll shuffle them one more time here. Let's see if we can get this right. Okay, so these are, again, a little difficult to shuffle if your hands aren't so big. So here we go. I'm going to take off the top maybe 4 or 5 cards. That's 5, I think. I'm going to close my eyes, and I'm going to mix them up. Now, you tell me when to stop mixing. You tell me when to stop. Okay. Now, you take one. And you take one. Okay. So I'm putting the other ones here. Now, I want you to look at your cards and remember the number, the value. If it's an ace, it's worth 1. If it's a jack, it's 11. Queen 12, king 13. I want you to remember the numbers, each of you separately, and the suit. So hearts look like that. Diamonds look like that. Let's see. Those are spades, and those are clubs. Okay? So you remembered your cards? You know your cards. Now, here comes the mathematics. You have to add up the two values, the numbers. So you have to look at each of those cards. If you have a 5 and you have a 3, that would be 8. So you add up the numbers, and then just tell me, well, first of all, let's lose the cards again. So please put one of the cards there. Now, a magician would already have that card. No, just one there, and we put the other one somewhere else. Okay. Now, a magician would already be able to find those cards, but I'm not a magician. I'm a mathemagician. So I'm going to use mathematics to find those cards. So all you have to tell me is, what do the two numbers add up to? What's the total number? 11. 11, okay. So if it's 11, it could be an ace and a 10. It could be a 9 and a 2. Many possibilities, right? It could be a 7 and a 4, 11. It could be 2 5.5s. It could be a 12 and a -1. And then there are irrational numbers. So there's infinite number of possibilities. But you said 11. Now, I couldn't help. Can I see your fingers again? Can I see your fingers? Yeah, I just want to check. Okay, can I see yours? Okay, I'm just looking at their fingerprints because I think I can find their cards by looking for their fingerprints. They forgot to wear gloves. You didn't wear gloves, right? So you left your fingerprints on the card. Very interesting. There's one. I found it right away. Let's see if I can find the other one. Okay. Fingerprints. Okay, I think I've got it. So, can you tell me, please, what your cards are? What was your card? 3 of spades, and your card was? Would it be this 3 of spades and that 8 of clubs? Thank you very much. Thank you. So that seems impossible, and it doesn't seem like it has very much to do with mathematics. So how is this possible? How is this possible? Okay, well, there's a secret. Actually, there's more than one secret. So the first thing is, when I said I was shuffling the cards, if you watch more closely, it's difficult here because these cards are so big, but I'm shuffling some of the cards, but actually I'm not shuffling all of the cards. I'm dropping a lot of cards on the top. from my right hand. So actually, many of the cards are mixed up, but the important cards on the top are not mixed up. I know what the top 6 cards are. So I cheated a little bit there by pretending to shuffle. So what could these magic cards be? And how do I know from knowing what the numbers add up to what they could be? Well, let's take a look at some possible cards. What comes after 1? 2? What comes after 2? 3. What comes after 3? 4. Now, is that a good idea? Wait a minute. 4 plus 1 is 5, and 2 plus 3 is 5. So if we use those cards and somebody says the card numbers add up to 5, I'm in trouble. So maybe we shouldn't use the 4. So maybe we should use 5. What comes after 5? 6. Well, yes, but if I use the 6 and somebody picks the 6 and the ace, the total is 7. But if somebody picks the 2 and the 5, the total is also 7. So I wouldn't know which it was. So maybe we shouldn't use that. What about 7? Well, that seems like a good idea, except 7 and 1 is 8, and 5 and 3 is also 8. So maybe we shouldn't use the 7. Maybe we should skip to 8. Maybe 1, 2, 3, 5, 8. What comes after 8? 9, yes, but haven't we learned our lesson? 9 plus 1 is 10, and so is 2 plus 3. We don't want to use 9. It turns out 10 is a bad idea. 11 is a bad idea. What is the right number to go for next? 1, 2, 3, 5, 8, 13. Have you ever heard of those numbers before? Well, actually, they're on the top of the deck here. Now, the order has been scrambled, but I can unscramble that. So I had a 1, a 2, a 3, a 5, an 8, and a king, representing 13. Do those numbers have a name? Are those famous numbers? Fibonacci numbers, right? And how do you get them? Well, if you add 1 and 2, you get 3. And if you add 2 and 3, you get 5. And if you add 3 and 5, you get 8. And if you add 5 and 8, you get 13. And you could keep going, but 8 plus 13 is 21. And my deck of cards does not have a 21. Maybe yours does. So for cards, we stop here. So at the beginning, what I did was, I pretended to shuffle, but I knew these cards. And then I did really let 2 people pick. And if you tell me what those add up to, I'm going to mix them up here with my eyes closed. Tell me when to stop. Stop, okay. So tell me, what do those numbers add up to? 13. So I instantly know that it's a 5 and an 8. That's the mathematics. Now, what are the suits? Well, I'm using the same 6 cards for about 8 years. So I remember the suits. I pick particular ones that I remember. So the suits is not mathematics, but the numbers is mathematics. So that's kind of how it works. And, oh, great, the projector works. But now, let us go back, please, to the slides. Excellent. Let's go back to the slides. Because on the slides, I go through this. So I call this the little fibs trick. In English, the word fib has a special meaning. It's like a lie that you tell maybe a small child to, go to bed or something will happen. That's a little fib, right? So we're using small Fibonacci numbers. So I call them the little fibs. So I shuffle the deck. 2 people pick cards. They remember them, tell me the number. They just tell me what they add up to. That's all I'm told. And I announce what the cards are. Well, this time I had them put back in the deck, and I pretended I was finding them using fingerprint. I was finding them using mathematics. So, as I said, one secret is that when several numbers are added up, you can figure them out from the sum if you're smart and use special numbers. And I did give a free choice of any 2 cards, but from 5 or 6 special cards. And I've already shown you what those cards are. So I keep those there, and I memorize the suits. So we use the Fibonacci numbers. 1, 2, 3, 5, 8, 13. They do keep going, but I'm not interested in the rest. In fact, they get very big very fast. And they have lots of interesting properties. But for the magic reason, you use a 1, which is an ace, a 2, 3, 5, ace, and a 13. Now, for an audience who knows the Fibonacci numbers, they might spot this. And there's other choices you can make. But if you've never seen it before, it probably looks good the first time. And I use these particular ones. And the suit order is clubs, hearts, spades, diamonds. It's a particular suit order that I can remember, sometimes called the chaste order. And if you take any two cards from those, there's this magic unaddition property that every total only works one way. Now, the total I was given was 13, which happens to be 8 plus 5, the sum of two Fibonacci numbers. What was I given? 13, yes, 5 plus 8. What was I given? 11. I was given 11, which was 3 plus 8. So how do you undecompose? How do you get back to the numbers? Well, the secret's quite easy. You always subtract the biggest number you can, the biggest Fibonacci number. So if somebody says 10, I think, well, 8's a Fibonacci number, so it must be 8 plus 2. If somebody says 14, I think, well, it's got to be the king plus the ace. I was given 11, so I knew 8 plus, well, the other one is going to be a 3. So that's how it works. Now, it doesn't have to be Fibonacci numbers. In fact, you can start with 2 and then 1 and add them to get 3, and then 1 and 3 adds to get 4, and 4 and 7 adds to get 11, which is a jack, and then you get 18, so you forget about that. That works, except we already saw 1, 2, 3, 4 as a problem, so just don't use the 2. Use 1, 3, 4, 7, and a jack. And if you do the trick a second time for the same audience, they'll be very puzzled, even if they know Fibonacci numbers, because you're now using different numbers. You have to remember the numbers and remember how to decompose. And you don't need numbers that are kind of in that pattern. 1, 2, 4, 6, and 10 work. And so does 1, 2, 5, 7, and 13. So it's an interesting question then, which numbers work and why? So you can explore that if you have time. Okay, so changing things totally, and this is for people who don't like cards. I have a picture here of several cans, and my question is, here's one of them. Which of these cans is very tall? And I mean so tall that the height is bigger than the circumference. There's the height and the circumference. And I'm looking at this now, and I've seen this one before, and my brain, my eyes, my brain think, that's pretty tall. So I think that looks like it's maybe 1.5 times, 2 times as tall as it is around. So we have many different cans here, right? We have the 2 tall ones, and we have some short ones. So the question is, for which of these is the height greater than the circumference? I think you'll agree that the small ones are not going to work. That one is certainly not tall enough. That one, maybe not. But that looks possible, and that looks possible, and certainly the 2 tall ones do. So I think, my brain thinks this looks about 1.5 times as tall. So who thinks this is about 1.5 times, or maybe twice as tall as it is around? Who thinks 1.5? Who thinks 2 times? 3 times. Yesterday in the high school, I had people thinking it was 3 times as tall. Okay, well, here's a little experiment we can do. We can take a piece of paper, and it just happens that this piece of paper is the right width. The width of the paper is as tall as the can. So if it's really 1.5 times taller than it is around, I should be able to rotate this page and wrap it around the can maybe 1.5, 2 times. So let's give it a try. We put the paper here and we try to wrap it around, and look what happens. It doesn't meet at all. So our brain and our eyes are wrong. At least my brain and my eyes are wrong. It's actually not tall enough that the height exceeds the circumference. Actually, if we were really smart, we might have figured this out without a piece of paper. Because what's inside this can? 3 tennis balls, right? I can't juggle, so I'm going to put them back in. But because there's 3 tennis balls in there, if I think about it, how wide is this? 1 tennis ball. How high is it? 3 tennis balls. What's the circumference? Well, you know, a teeny bit of geometry. The circumference of a circle is pi times the width. So the circumference is pi tennis balls, and the height is 3 tennis balls. So the question then becomes, which is the bigger number? 3 or pi? Pi. How many decimals of pi do you need to know to get this right? None. None. It's 3 point something. That's all you need to know. So that's a good one to try on somebody who says, oh, I know 50 decimals of pi or 2,000 decimals of pi. Try this and see if they really understand pi. It's a very easy thing to get confused about. Okay, so it turns out the answer is none of them. Now, when I first went to visit Martin Gardner, within 5 minutes, he brought out this tall, skinny glass, and he said to me, do you think this glass is taller than the circumference? And there it is. It looks really tall and skinny. And I said, of course. And he took a piece of paper and showed me that I was wrong. So that inspired the tennis ball puzzle there. We're very bad at judging circumference or girth. We're just not good at it. Okay, so we got one more card trick for you. And for this, we'll go back to the projector here, please. And I need somebody, maybe somebody young who likes ice cream. Is there somebody young here who likes ice cream? A lot of young people back there. Well, just if one person could come forward, please. One person who likes ice cream. Let's go. One person who likes ice cream. Oh, boy. This is fun. Okay. Come, please. Thank you. And he's got a Guinness shirt on. Okay. Let's do a photo up here. This man has a Guinness shirt on. I'm from Dublin. So what is your name? Alexander. And your favorite drink is Guinness? Good, good, good. Okay. What's your favorite ice cream flavor? Chocolate? Can we do chocolate? Okay. Chocolate. He likes chocolate. Very, very intelligent man. He likes chocolate and Guinness. Okay. Now, chocolate. I've done chocolate before. I've also had a Guinness, I think. Chocolate has 9 letters in it, in English. Chocolate has 9 letters. So what would, if chocolate is 9, what would twice chocolate be? 2 9s? 18, maybe? 18. So we need enough cards to spell out the word chocolate, which is 9, and a few extra, but no more than 18. So I just have between 9 and 18 cards. So can you mix those up, please? Mix those up. So we'll do the little experiment over here. So mix them up, okay? So he's going to get 3 scoops of chocolate ice cream and 3 toppings. In a virtual, imaginary sense, okay? Just like the Guinness you drink, right? It's imaginary, good. Okay, so here the cards are. They're mixed up. So come on over here, please. And we'll try this here. So we're going to spell out C-H-O-C-O-L-A-T-E for the first scoop and then the first topping. And you would twice more. Don't worry, it's low calorie. It's okay, it's good for you. C-H-O-C-O-L-A-T-E. Second time. Have you done magic before? No, he has not done magic before. I think he's going to do magic tonight. Here we go. C-H-O-C-O-L-A-T-E. Okay. Now, I'd like you to press down hard, Alexander. Press down with your fingers here and concentrate. Press down hard. And I want you to think about 6 bottles of Guinness. No, sorry. I want you to turn that top card into the 6 of spades. Can you do that for me? Turn it over. Is it the 6 of spades? Turn it over. Turn it, let's put it back so we can all see. It's the 6 of spades. He's incredible. It's his first time. Give him a round of applause, please. Thank you. Okay. So you can do this trick too. In fact, anybody can do this trick. And I'm going to explain now what's going on. So let's go back to the slides, please. Okay. So, well, I predicted, right? He was going to say chocolate, right? Many people say chocolate, but it works with any flavor. If you say vanilla, that's 7 letters, so you need between 7 and 14 cards. Strawberry is 10 letters, so you need between 10 and, what's twice 10? 20, between 10 and 20 cards. It's important to get the mathematics right. So I take the cards back, and I had about a quarter of the deck, and they were mixed up. He shuffled them, and then I spelt out and dropped. And at the very end, we do it 3 times. We always do it 3 times. And at the end, I said, you know, the cards were mixed. You picked the flavor. I didn't influence you. But I want you to press down hard on the top card. And in the slide, it says the 4 of spades. This time, I said the 6 of spades. But I say something, and he presses down, and that's the card. So do I really make him turn it into that? Probably not. Maybe I know it's going to be that card because of the power of mathematics, which enables me to predict what card's going to be on top. So how could I possibly know? I gave him the cards, he shuffled them. Now, if you were looking, when I got the cards back, I did a little more shuffling, and I stepped back like this. And the last thing I did before I started dealing, and I did it in front of 200 people? I looked at the bottom card. But I looked at it this way, so you probably didn't see. So I can see now it's the Jack of Spades. The mathematics brings the bottom card to the top, I promise. And I don't know how many cards I have. It doesn't matter. That's enough for a vanilla, chocolate, strawberry. It doesn't matter. So you can have more or less, for vanilla, no more than 14. For strawberry, no more than 20. So there's a mathematical magic property that brings the bottom card to the top, which is very surprising. And I'll explain it to you in the following way. I can give you different explanations of it, but it works for the following reason. Imagine you start with the cards ace, 2, 3, 4, 5, 6, 7, 8, 9, maybe stop at 11, which is a jack. So you have 11 cards in order, perfect order. When you do the deal 3 times, the bottom card comes to the top. And I'll show you a picture version of why. I can explain it using algebra, but we're running low on time, so let me show you the picture version. But let me first talk about, again, what happened here. This was actually published in honor of Martin Gardner's 90th birthday back in 2004, and there's a number file video. Number file is a very good mathematics video channel. You should all be looking at it if you're interested in mathematics. There's a number file video of this trick, and it explains it in some detail. So, well, you're counting out, which means reversing the order and dropping the rest on top. So if you try and track it mathematically, you get something like this. And I did this the first time I was trying to figure it out, and then I just scratched my head and I said, I don't understand this. This is true, but I don't see what's going on. I don't see why, after 3, the bottom card comes back to the top. So let me show you a different approach to it. And this is the picture I'm going to show you here. So what actually is happening is the following. When you start, imagine that's an ace, a 2, a 3, a 4, down to a king. So that's in colors, just in shades of gray, a representation of 1 through 13. And suppose we do mint chip, which is 8 letters. So mint chip is this, first 8. So you spell them out by putting the first card on the bottom and the next card. So you're reversing the order of 8, and then you drop the rest, which I think is 5. 13 is 8 plus 5. So you've got 8 cards representing the flavor name, and 5, which is the rest, and you reverse the order of those and drop the rest on top. Actually, 5 and 8 are interesting numbers, but what's really important is 13 is 5 plus 3 plus 5. So you think of the top, the middle, and the bottom. And the first time you do it, you get this. And the second time you do it, you take those cards and flip the order, and they go there, and that gets dropped on top. And the third time you do it, look what happens. You reverse those guys, they go there, and that gets dropped on top, and that card is that card, is that card, is that card. That's the one that used to be at the bottom. So the bottom card goes to the top. And what I didn't tell you, but this picture tells you, is that if you did it 4 times, which is more work, if you do it 1 more time, you reverse the order of those and drop that on top, and look, it's the same as where you started. So it's an interesting mathematical thing called a permutation. If you do it 4 times, it's like you didn't do it at all. It's like turning 90 degrees 4 times, you're back to where you started. It's not a rotation, it's a little more sophisticated, but it has some interesting mathematical properties. So that's why it works. Okay, now, Mathematics and Magic and Mystery was the name of a famous book that Martin Gardner published in 1956. A wonderful book, still a wonderful book, very cheap. I know it was published in Russian. I suspect it was published in Serbian. And in 2014, for his 100th birthday, he didn't live to see it, there's a Mathematics Awareness Month. Now here it's May. In America, it's April. And this was a poster and actually a web page that honored this concept. And if you go to the web page for Mathematics, Magic, and Mystery for 2014, you will find a web page with 30 days in April. Each of those is a different activity with videos, and there's some mathematical magic, there's rope tricks, there's juggling, all the things that Martin loved. So 30 activities that you can explore, or if you're a teacher, you can use with your students. So it's a good thing to investigate. I wrote to him in the year 2000, and I sent him some stuff I'd written up, and he was very kind, and he wrote back and he said, you should write a book. And that was not a good idea in 2000, because I didn't really know much about the subject. But I learned more, and I invented some tricks, and then 4 years ago, I did write a book about mathematical card magic. And I wish he was alive to have shown it to him, but he was very helpful, and he encouraged me a lot. I didn't start doing magic till I was, later in life. The people who are good at magic start when they're 12 or 14 or 10. I started much, much later. So I have to rely on mathematics to make my magic work, not sleight of hand. So earlier I had an assignment to come up with a list of 52 items. And just like Ben, I'm prepared to hand over all the cash in my wallet if anybody has finished this task. Did anybody finish? Did anybody get halfway there? If you get a tenth of the way there, I'll give you all the money I've got. Even 1%. 1%? No? Well, what could the problem be? Well, here's the problem. If you check your list to make sure everything's on it, you find it should have 52 factorial items. And there's the number. You can see it here. It's obviously finite. It's got a lot of digits. It's actually about 8 times 10 to the 67. And the problem with that number is that it's bigger than the number of elementary particles in our galaxy, which means there isn't enough paper in this room, or in Belgrade in general, or in Serbia, or in Europe, or on this planet, to write it all down, even if you had the time. There's just too much. So the number of ways of mixing up cards in a deck is unbelievably large. Even though we can write that number down, and we can write down much bigger numbers very easily, it's inconceivably large. It's a very big deal indeed. And there are some interesting consequences. Imagine 2 seeds were released from the top of a windy mountain on different days, wind blowing different directions. Do you think those seeds would end up in the same place? Pretty small chance, right? So I would say a very small chance that they ended up in the same place. But that number, that chance, is huge compared to the probability that if you take 2 decks and send them out into the world for a few weeks so they get thoroughly shuffled, that they would have the same order. And as a matter of fact, I hope there's some cameras here because we have a very unique opportunity here. I have here a deck of cards which has been shuffled many times, and I would bet 1,000 anything, 1,000 Tesla cars if I had them, I would bet all the money in the world that this order has never occurred in any deck of cards in the history of the world, ever. You're seeing something here that's never been seen before. It's very hard to wrap your head around that, but it's true. With high probability, it's true. Very, very surprising. Okay, let's wrap it up. One last puzzle. Here we go. I want you to wrap up this yellow cube with the blue paper. So the yellow cube is 1 by 1 by 1. The blue paper is 3 by 3. Now a cube has 6 sides, so you need 6 square units of paper. You have 9, so you have extra. But if you try folding up the paper, it doesn't quite meet at the top, and there are some rules. You have to completely fold the cube in the blue paper, and you're allowed to cut or fold, but it's along the grid lines. You notice there's 3 by 3 grid lines here. There's these lines, so you can't cut diagonally. You have to cut along the grid lines. Well, you could just cut it into 6 pieces, right? And just stick 6 of them on the side and have 3 left over. But that's not allowed either. When you're finished, the piece of paper must be in 1 piece. You can cut it, but it has to stay in 1 piece. It's a very interesting problem. It's on a Russian website. I found it 4 or 5 years ago. The answer is very surprising. Don't Google it. Try it. That way your brain will work better. Thank you very much for your time.